Hello everyone, welcome to my presentation on the topic virtual block mining and hybrid consensus mechanisms. Before we start diving specifically what does those terms mean, I would like to begin with a definition like proof of work and the problems which are related to it. Proof of work is a consensus algorithm which is based upon miners trying to solve a cryptographic challenge. While doing this, miners compete between each other to be the first one to solve it, as the winner of this race will get a reward. The idea behind that is that given a specific hardness condition H and the hash of block data, miners try to find a nonce such that the hash of concatenation of nonce and block data is less than specific target value, which is calculated based on the hardness condition. From this, we can define a few problems related to proof of work. The first one is that the machines with more power resources have higher chances of finding a solution as they have higher hash rate. Because of the hardness condition, which is also adjustable every 2 weeks, depending on different factors like for instance number of miners, it is not easy to find a solution for this cryptographic challenge. On average, it takes around 10 minutes for a new block to be mined and added into the blockchain. To increase the chance of winning this solving race, people start building mining farms and investing a lot of money in buying the latest and better hardware equipment. The second problem which arises here is that all this equipment needs a large amount of electricity. And the third one is that besides all of this, many miners can cooperate, forming so-called mining pools, what in practice makes proof of work more centralized than decentralized, as the probability of 51% attack is higher with mining pools. So what can be done, or what consensus protocol can be used which would give us more decentralized blockchain, will not depend on the hardware and would use less energy power. Here we come to the term process of virtual mining. Why is it called like this? The reason for that is that the protocols which try to achieve it do not require any resources except money, which each node holds. The best example of such protocols is proof of stake, and in proof of stake there are no miners and no mining, but validators and validation. So proof of stake is an algorithm where the next block miner, in the case of proof of stake validator, is chosen randomly from a set of validators. To become a validator, the node has to put some money as a deposit. A validator does not lose his money until it behaves maliciously. There are many algorithms on choosing a random validator, but with every blockchain, this implementation varies a little bit. At some blockchains, a validator with the larger deposit can be chosen. In another, validator is selected whose money are held as a deposit the longest time. What happens if the validator behaves maliciously? If the validator tries to validate the non-valid transactions in the block and add it to the blockchain, then all his money that are staked will burn. So the validators are encouraged to behave honestly. If the node would like to not be a validator anymore, then the node gets all his money back after some time. It is not done immediately, as the blockchain has to prove that the node hasn't approved any non-valid block. Now let's look at few implementations of proof of stake. The concept of proof of stake was first proposed by Peercoin, and it was a modification of proof of work in a way to decrease amount of energy resources needed to solve the cryptographic puzzle. Peercoin uses such metric like coin age, amount of time, how long do the coins are owned by each node. Miners, while solving the challenge, could consume their coin ages to decrease the difficulty of puzzle. It is implemented based on tracing all unspent transaction outputs and analyzing how much time the unspent values are stored at each node. Another example for implementing pure proof of stake without proof of work is to follow the coin algorithm. In this algorithm, we consider that all coins are indexed. Additionally, we have our blockchain and the coins. Red arrows show us the time where the coins were in use last time, specifically where the coin is in unspent transaction output. Also, we have nodes which own a specific coin. So what does this algorithm do is that it takes a hash of a header of block t-1, and this hash can be used in randomizer. This randomizer returns a random token indexed based on hash, which is used to look for the next block validator. All blocks are traced back to the minting block which created this token, or token owner, based on unspent transaction output, and the owner of this token is chosen as a validator for the new block with index t. All of that seems good, since proof of stake does not require the node to have expensive equipment and it does not consume a lot of electricity. It is still not a perfect consensus protocol. It has its own drawbacks, and specifically there are two attacks which can be done on blockchain, which use proof of stake: nothing at stake attack and grinding attack. In proof of work, it is considered that the miners should add the block to the longest chain. When the forking happens, the miner should decide to which fork the miner should add the block. Let's consider that the node has added the block to wrong branch. In case the other branch ends up on winning, the miner loses his money, and specifically the cost for electricity, which we use to mine the block, and also the reward for the mined block. In the proof of stake, on the other way, the validator can extend all branches when there is a fork. Choosing wrong fork is not costly for the validator at all, but can cause problems later. That's what is called nothing at stake attack. Let's consider that we have node A, which pays some coins to the node B. Node A creates two transactions. The first one is honest transaction, where node A sends coins to node B, and at the same time, node A creates malicious transaction where node A pays coins back to himself. When node A will be chosen as a validator, he will add honest transaction to one branch and false transaction to another branch. Later, the other nodes will add blocks to all branches because there is no long branch, and as said earlier, other nodes do not lose anything by adding blocks to all branches of fork. At some point of time, node A will be chosen as validator again, and he will be able to add new block to the branch which contains false transaction, what in the end gives him his money back. Another attack is grinding attack, and it is likely to happen in proof of stake protocol. With proof of stake, the block leader is usually determined before a round of mining starts. In this case, the attacker can try to influence the leader election process before validation of block to improve its chances of being selected in the future. When the random generator takes as input the header of the most recent block for leader election, the attacker may test several possible block headers with different content to improve the chance of being selected in the future. Additionally to that, there are other issues related to proof of stake. 51% attack is still possible when the node will deposit more than the half of all money which were deposited by all nodes. But this attack is less probably to happen, but it also depends on the market value of cryptocurrency. Also, the randomizer has to choose block leader more carefully. It cannot be absolutely random because of the stakes, and it also cannot depend only on the stake, as it will favor only the richest nodes. Now let's look into hybrid consensus protocols and why do we need them. Permissionless consensus protocols like proof of work or proof of stake have a big problem of performance because of the scalability performance trade-off. To improve that, it is recommended to combine a permissionless with fast permissioned consensus mechanisms. Bitcoin NG has a feature of decoupling leader election and the transaction serialization. What does that mean? Bitcoin NG contains two types of blocks, key blocks and microblocks. Key blocks do not have any content and use proof of work for leader election. However, operation decoupling in Bitcoin NG does not ensure strong consistency. The algorithm of Bitcoin NG allows to process transactions and mine new blocks in a very short time. After the next block leader is chosen via proof of work, the leader publishes in epoch time microblocks with limited rate and size, which are used for transactions realization. Epoch time is a time between two published key blocks, what in Bitcoin blockchain, for instance, is equal to around 10 minutes. Another blockchain called peer consensus consists of proof-of-work-based scheme, which is called blockchain, and BFT-based scheme, which is called chain agreement. Peer consensus works in a way that the nodes get the voting right in chain agreement stage while proposing new blocks in blockchain phase. Then there are 4 stages: propose, pre-prepare, prepare, and commit, during which the miner for the next block is chosen. Then miner proposes one of the blocks, which were generated during blockchain phase, and other miners try to validate the blocks. As soon as the block is validated, it is added to the blockchain. The last protocol to review is Hybrid Consensus Protocol. In a Hybrid Consensus Protocol, the data framework of 2 type blocks in Bitcoin NG and the hybrid POV BFT design in peer consensus are combined. In order to add new blocks into the blockchain, the BFT committee is selected from so-called sliding window. The BFT committee is maintained by a fixed size sliding window over the proof-of-work based blockchain. The sliding window moves forward along the blockchain as new blocks are abandoned. When the committee is chosen, they choose the transactions from the so-called transaction pool, the pool of outstanding transactions, and include them into the new block. A new block is added immediately to the blockchain.